So we've talked about RC circuits. No, yes, we talked about RC circuits. We talked about LC circuits. Now let's talk about LR circuits, circuits with inductors and resistors. So let's say we have a circuit with a battery, a resistor, and an inductor, and a switch. The switch has been in position A for a long time. So if this is the case, then what's happening in the circuit, if the switch has been in position for a long time, it means that current is constant. If current is constant, then if we think about the inductor, so the potential difference across the end of the inductor, which is due to the change in current, that's going to be equal to 0. And the potential difference, which is equal to the current times the resistance of the inductor, is going to be 0 because the resistance of inductors is approximately 0. So all of the potential in this circuit is across the resistor, and the current is going to be given, so the flowing current is going to be given by I equals V of the battery divided by the resistance R. So when the switch has been in place for a long time, there's no potential drop over the inductor. It's like it acts like a short circuit. You could just as well take it out and replace it by a piece of wire. We'll talk more about that in a bit. Okay, so what if we then take our switch and we flip it to B? What happens then? So I've got a new picture. If we flip the switch to B, so we flip it down to B, it means the battery is not connected to the circuit anymore. We've opened up the part with the battery in it. So the battery is not part of the circuit anymore. Without the inductor, the current would immediately go to 0. But the inductor opposes that rapid change in current. So the current I will decrease to 0 over time. What that means is that the inductor acts like a battery just for a little while. So our task will be, let's find the current as a function of time as it drops to 0. So we'll start by writing Kirchhoff's law, which says that the net potential around the circuit is equal to 0. The net potential around the circuit will be the potential drop across the resistor, so the potential difference of the resistor, plus the potential difference of the inductor, and that has to be equal to 0. Across the resistor, there is a potential drop, that's minus IR, and across the inductor, the expression for the change in potential is minus L times dI by dt. That's going to be equal to 0. Our question is asking, what is the current as a function of time? So let's think about what we know here, just conceptually. Does it make sense that both of these are actually negative? If the current is decreasing, and that's what's happening in our circuit, if the current is decreasing, di dt is actually going to be negative, which gives us a negative times a negative, gives us an positive potential difference across the inductor. So this does make sense. Okay, let's start to solve for our current. We'll start by bringing L di dt to the other side. So L di dt equals minus IR. Let's divide both sides by I. Now I'm going to divide both sides by L. I suppose I could have done that all in the one step, couldn't I? And now I'm going to bring our dt to the other side. 1 over I di equals minus R over L dt. And let's see, I think I'd like to just change this because this is reminiscent of something we've seen before. I'm going to say minus 1 over L over R dt. Okay, so I just multiply top and bottom by 1 over R. So if I want to find my current, I'm going to integrate both sides. So the integral from our initial current to some final current of 1 over I di. So this is going to give me the current at any time t, is equal to the integral from 0 to some time t of minus 1 over L over R dt. The integral of 1 over I is the natural log of I. That's going to be evaluated at some current I, and our initial current equals minus 1 over L over R of t evaluated at some general time t and 0 gives us natural log of I minus natural log of I 0 equals minus 1 over L over R times t. And let's see, this page is a tiny bit full. I'll just get a fresh sheet. So now my next step is, if I'm subtracting two natural logs, I can just divide the arguments. Natural log of I over I 0 equals minus 1 over L over R times t. To get rid of my natural log, I'll raise both sides to the exponent e. So e to the natural log just gives us the argument. E to the minus 1 over L over R times t. Okay, this looks a little bit familiar. I'm going to define tau equals L over R as the time constant. And we did this for an RC circuit as well. And I0 is our initial current. That gives us that our current as a function of time is our initial current e to the minus t over tau. So our current falls off as a function of time. We could plot that if we wish, and it falls off exponentially. So we have our current I on the vertical, we have our time t on the horizontal. It starts with some maximum value of I0, and it dies off. Technically it takes forever to get to 0, just like the current in an RC circuit, but practically it gets pretty darn close to 0 at 5 times the time constant. So this is just like the current in an RC circuit. So similar behavior there.